I kind of call this the gloom and doom section because really section 4.4 talks about all the bad things that can go wrong when you're doing testing, or like the problems that you can have when you're doing hypothesis testing. But we will also talk about how to kind of combat those things as well. So it's not like all doom, but it is a little gloomy. And the example that we're going to be looking at a lot today has to do with this study they did to figure out if the choice of mate improved offspring fitness in fruit flies. And I think this study is fantastic because I think it's hilarious, actually. Like, I don't know who sits around and thinks of doing studies like this, but basically what they were trying to find out is, you know, if a fruit fly gets to choose who they hook up with, like, are they going to produce baby fruit flies that are stronger than if they were forced into an arranged marriage, essentially. And that's what they're looking at here. So the first study that was done, it was published in Nature magazine, and they said they had a p-value that was less than 0.01. So that's pretty significant. And they concluded, based on their data, that if you got to choose your mate, then your baby fruit flies were going to be more fit, meaning that they were going to be able to withstand the enemy better. And apparently, everybody knows that you know, the fruit flies don't care who they mate with. So this went against conventional wisdom, the conventional wisdom that we all know about fruit flies. Maybe it's conventional wisdom among researchers. So then some other researchers came along and they were like, wow, that's interesting. That kind of goes against what we thought. You know, let's see if we can replicate these results. And so they set up a new experiment to test this. And this is how their new experiment worked. They took 600 female fruit flies and they divided them into two groups. So half of those fruit flies got put in a cage with 900 males. So they got to choose whoever they wanted to mate up with, okay? And the other 300 were placed into individual vials with only one male. So they were the arranged marriage fruit fly. So they got just stuck with whoever they were stuck with in order to mate with. And after everybody was done mating, doing whatever fruit flies do, then the females were separated from the males and they were put into these egg-laying chambers. And then they took the larvae from each of these chambers and then they placed them into a cage and they let loose a whole bunch of mutant flies on them. Just to, these are the bad guys. So they're going to come in and attack the larvae. And then the researchers are going to measure like who survived in the end. So which larvae were like the strongest to be able to withstand these mutant flies. Sounds kind of violent, doesn't it? And they did this 10 times a day for 5 days. So this whole thing with the 600 fruit flies, splitting them up, doing all that stuff, they did that 10 times a day for 5 days. And so here's kind of a picture of what happened. So they took everybody, they split them into two groups. One set of females got to choose whoever they wanted to, and one set of females got stuck with just one. Then they let them go off and lay all their eggs. Then they released the mutant flies, and then they counted how many survived. So here's what happened. 6,067 of the 10,000 mate choice larvae survived, and 5,976 of the 10,000 no mate choice larvae survived. So the difference in proportions for the choice versus no choice on the mate ended up being 0.009. And so here's a randomization distribution for that. And you can see that based on our randomization distribution, the p-value for this was 0.102. And we gave kind of some standard levels for alpha last time, 0.1, 0.05, 0.01. And this is larger than all of those. And so if P is high, then we would keep the guy, meaning we fail to reject, and we would say we do not have evidence that, you know, whether or not you get to choose your mate has any effect on how able your larvae are at rejecting or at battling off the mutant flies. So now we have two studies that were done. One study, the one that they published in Nature magazine, found significant results. And the other study that they did to try to replicate it found insignificant results. So what happened here? Like, what's going on? So they seem like they conflict. And basically, anytime that we do a hypothesis test, since we're just basing our decision off of sample data, then it's possible that we could make a mistake. And there's essentially two kinds of mistakes that we could make, okay? And we call those type 1 and type 2 errors. So let's talk about what a type 1 and type 2 error are. So a type 1 error is going to be if we reject the null hypothesis when the null hypothesis is actually true. All right, so we'll be making a type 1 error if we rejected the null hypothesis when the null hypothesis is actually true. The other type of error is a type 2 error. And a type 2 error is going to be failing to reject the null hypothesis when the null hypothesis is actually false. So type 2 error is failing to reject the null hypothesis when the null hypothesis is actually false. Okay, so those are the two types of errors that we can make in sampling here. So I know on your notes page, there's a bunch of different things in there. We're going to kind of fill those in as we go. So I'm not going to give you my memory trick yet. I'm going to tell that to you in a minute. But in your notes, I want it to be organized a certain way. Well, I think it would help you if it's organized a certain way. Maybe I should say that. Whoops. So we'll eventually fill in all those bullet points and the memory trick. So no worries. Okay, so let's look a little closer at what this type 1 and type 2 error means. Okay, so in a test, when we do a hypothesis test, there's basically 4 possible outcomes. Okay, and so we're breaking those down by what the actual truth is, you know, whether or not the null hypothesis is actually true or false, and what the decision that we make in our test is. So if the null hypothesis is false and we reject the null hypothesis, then we're making the right decision. So everything's good. Null hypothesis was false. We rejected it. Good job, us. Okay. If the null hypothesis is true and we don't reject it, then we're also making the right decision. So again, you know, good job, us. So null hypothesis true. We didn't reject it. We made the right choice. Now here comes in where we can make mistakes. So if the null hypothesis is true, but we reject it, our decision in our hypothesis test is to reject it, that's when we're making a type 1 error. Okay, so type 1 error is the null hypothesis was really true, but our decision in our test was to reject it, so we made a type 1 error. And the other type of error we can make is if the null hypothesis is false, but we don't reject it, then we're making a type 2 error. Now, of course, in real life, you know, we're just basing our decision off of our sample data, and we won't know if we made one of those types of errors because we don't actually know whether the null hypothesis is true or false. In order to know the absolute truth of the null hypothesis, we would have to measure everybody in the population because we would have to know what mu was or what p was or whatever our population parameter is. So in real life, we're not going to know. We're not going to know whether or not we made one of these errors. But it's a good idea to be aware of what kind of errors we could be making and what that would mean. So here's another way to look at type 1 error. So type 1 error is rejecting a true null. So it's like getting a false positive. And a type 2 error is not rejecting a false null. So it's like a false negative. So really these type 1, type 2 errors, they have a pretty good counterpart with our legal system. So in our legal system, if you're accused of a crime, then you're considered innocent until proven guilty. So a person is innocent until proven guilty. So the null hypothesis is innocence, and then proven guilty would be the alternative hypothesis. So guilty is the alternative hypothesis. Innocent is the other hypothesis, the null hypothesis. And then when we're in a court of law, then we must show evidence beyond a shadow of a doubt in order to say that the person is guilty, right? So, you know, they go to the jury has to be unanimous. They have to decide that, yes, this person is guilty. The evidence has shown us beyond a shadow of a doubt that this person is guilty. So the evidence in our hypothesis test, of course, is the p-value. And the smaller your p-value, the greater the evidence you have, and kind of that cutting point where we're like, okay, now it's beyond a shadow of a doubt. That is our significance level, our alpha. That's where we're kind of making that decision. Yep, you know, it is. We have so much evidence that we're going to say that the alternative is true. But just like with our hypothesis test, there can be mistakes that are made in our court of law, right? So we could convict an innocent person, or we could end up releasing a guilty person. So those are the two errors that we can make in our legal system. So convicting an innocent person would be like making a type 1 error. So basically concluding they're guilty when they're actually innocent. And then releasing a guilty person would be like a type 2 error. So that would be, you know, saying we don't have enough evidence to convict them, but really they were guilty and we should have convicted them. And I'd like to say that we don't make these errors in our system, but we all know that these errors are made enough times that it's not good. So here is a little meme that I liked about type 1 and type 2 errors. Okay, so type 1 error is like a false positive. So it's like this doctor telling this guy, hey, you're pregnant. So clearly that's an error. And then type 2 error is like a false negative. So it's this doctor telling this lady, yeah, you're not pregnant, when clearly she is. All right, so back to our study here. So here's, you know, we had these 2 studies that were done and they had conflicting results. So here's the possible options for why we got those conflicting results. So one option is that the original study, the one that was published in Nature magazine that said it had a p-value of less than 0.01, maybe they made a type 1 error. So maybe they rejected when really the null hypothesis was true. So that's one possibility. Another possibility is that the second study made a type 2 error. So they failed to reject, but maybe the alternative was really true and, you know, that was an error that they made. They should have rejected. Or a third option is maybe no errors were made, but the experimental settings were so different that they yielded different results. So here's another example. A new blood thinning drug is being tested against the current drug in a double-blind experiment. Is there evidence that the mean blood thinness rating is higher for the new drug? So use N for the new drug and O for the old drug. So which of the following are the null and alternative hypotheses? So what do you think? From this list, what would be the null and alternative hypotheses for this test that they're talking about here? All right, I see a lot of votes for C over there, and that is correct. So this is a test of 2 means. We're comparing the old drug and the new drug. So in the null hypothesis, they're going to be equal. Equal sign always goes in the null hypothesis. And the alternative hypothesis, it said that, is there evidence that the mean blood thinness rating is higher for the new drug? So that's higher is code word for greater than. So we're gonna have greater than in the alternative hypothesis. And something to remember is that our hypotheses are always written about parameters, never about statistics. So like D and E down here are super wrong because they have X bar in them, and we should never have X bar in the hypotheses. All right. So now let's think about type 1 and type 2 errors in the context of this problem. So we have this new blood thinning drug. We're testing to see if the new one is greater than the old one. So what would a type 1 error mean in this situation? So if we made a type 1 error, what would that mean? Error is rejecting the null hypothesis when the null hypothesis is true. So that would mean that in our study, the decision we would be making would be to reject and conclude that the new drug is better, when in reality, there's no difference. It's really not better. So when we're kind of describing what a type 1 or type 2 error means in the context of the problem, we're always going to say it like, okay, making this conclusion in our test when really this is the truth. Okay, so we're going to kind of look at both of those. So that's what it shows here. So we find evidence that the new drug is better, so we rejected, when really it's not better. So in other words, the truth is that the null hypothesis is true. Okay, what about a type 2 error? If we made a type 2 error, what would that mean in the context of this problem? Okay, good. Yeah, D is the correct answer. So a type 2 error is failing to reject the null hypothesis when the null hypothesis is false. So that would mean that the decision we would make with our test would be failing to reject, so not having enough evidence to conclude that the new drug is better. And then the reality would be opposite of that. So the reality would be that it really is better. So it would be failing to conclude that the new drug is better when really it is better. Okay, so let's think about the probability of a type 1 error. Okay, so remember, type 1 is rejecting the null hypothesis when the null hypothesis is true. So if I look at a randomization distribution for my test, remember this shows me possible sample statistics I could get if the null hypothesis is true. So if the null hypothesis is true, 5% of these dots are going to be in the most extreme 5%, right? Because just by definition, the 5% most extreme are in, there's going to be 5% there. It's kind of like saying 5% equals 5%, okay? So that means that 5% of statistics are going to give p-values that are less than 0.05. And remember, we said, okay, you know, if my alpha is 0.05, then I'm going to reject if my p-value is less than that. But based on this distribution here, remember, this is what could happen if the null hypothesis was true. So these values out here that we would be rejecting for, they would be unlikely to occur if the null hypothesis is true, but they still could occur. And in fact, they would occur about 5% of the time. So we would be rejecting the null hypothesis, even though it was true for 5% of all possible values. So that means 5% of statistics are going to lead to rejecting the null hypothesis if our alpha is 0.05. So that means that if alpha is 0.05, there's a 5% chance of a type 1 error. Okay, we can see a similar thing if we use an alpha of 0.01. So if the null hypothesis is true, 1% of statistics are going to be in the most extreme 1%. 1% of statistics are going to give p-values that are less than 0.01. And we're going to end up rejecting the null hypothesis 1% of the time, even if the null hypothesis is true. So that means that if the null hypothesis is true, there's a 1% chance of making a type 1 error. Okay, so probably you're noticing a pattern here. If alpha is 0.01, there's a 1% chance of making a type 1 error. When alpha was 0.05, there was a 5% chance of making a type 1 error. You can see the pattern here. Then let's say my alpha was 0.10, then there would be a 10% chance of making a type 1 error. So basically the probability of making a type 1 error is equal to the significance level, alpha. So the probability of a type 1 error is just alpha. It's the same as the significance level. All right, so now, like in your notes, I'm going to go back and I'm going to give you my memory tricks, and I'm going to tell you a couple other points about type 1 and type 2 errors. All right, so first I'll tell you my memory tricks. Okay, so for a type 1 error, I use the memory trick ART. Okay, so ART, the A in ART stands for alpha because alpha is A in the Greek alphabet. And alpha is the probability of making a type 1 error. Okay, and type 1 error is going to be rejecting H naught when H naught is true. All right, so you can see where the kind of the A and R come from here? So the R here, oh, I gotta switch back to that's what I gotta do. Okay. So the A stands for alpha, probability of a type 1 error. And then the R stands for rejecting H naught when H naught is true. That's where the art comes from. Okay, my second memory trick for a type 2 error is BFF. Okay, and the probability of making a type 2 error is beta. And we're not actually going to talk about how to calculate beta or anything in this class. It's a little bit complex. It depends on sample size. It depends on a lot of things. So we're not going to specifically talk about it in here, but that's where the B comes from. So, and then the FF comes from failing to reject H naught when H naught is false. So I'll underline that stuff here. Just a second. Put that over there because once I click on something else, it won't let me move it anymore. Okay, so type 2 error. Then this beta, it comes from the Greek letter, or it represents the Greek letter beta, which represents the probability of a type 2 error. You don't actually have to know that part. But type 2 is going to be failing to reject the null hypothesis when the null hypothesis is false. So notice when we're talking about these errors, we're always referring to the null hypothesis. All right, a couple more things. When I think about the probability of a type 1 error, the probability of a type 2 error, they have an inverse relationship. Okay, so it's like they're sitting on two sides of a scale. So if I reduce the probability of a type 1 error, that automatically makes the probability of a type 2 error go up. Okay, and if I reduce the probability of a type 2 error, that's going to make the probability of a type 1 error go up. So these errors, they have an inverse relationship. Because of course, ideally, we don't want to make any errors. Nobody likes to be wrong, right? But there's a little trade-off here. Type 1 and type 2 errors have an inverse relationship. Reducing the probability of one type of error increases the probability of the other type of error. So type 1 and type 2 errors have an inverse relationship. Reducing the probability of one type. So reducing the probability of one type of error increases the probability of the other type of error. All right, and if I want to somehow simultaneously decrease the probability of both kinds of errors, the only way I can do that is by increasing the sample size. So the only way to simultaneously decrease the probability of a type 1 and type 2 error is going to be to increase the sample size. So that's kind of our favorite response to everything in statistics, isn't it? Let's just take a bigger sample size. Bigger sample size solves everything. Actually, we're going to learn by the end of the class that bigger sample size does not necessarily solve everything. Okay, so let's think about how we interpret or how we explain a type 1 or type 2 error in the context of the problem. And I kind of mentioned this previously, but basically when we're trying to explain an error in the context of the problem, it's going to be something like concluding that, and then you're going to fill in whatever you concluded with your hypothesis test, when really, and then you're going to fill in the truth, which is going to be the opposite of whatever your conclusion was in your hypothesis test. So here's a couple of examples. So for a type 1 error, that might be concluding that Pizza Hut delivery times are longer than 30 minutes on average, when really they are not. Or example for explaining type 2 error would be concluding that we do not have evidence of a difference in average time it takes to get ready for males and females, when really they are different. So saying what you conclude and then saying how the truth is opposite of what that is how you're going to describe those. Okay, so on your notes page, there's a little example that is called BPA in tomato soup. There's 4 questions there that talk about describing what type 1 and type 2 errors mean in those situations. So I'm actually going to put you guys back into your breakout rooms and let you guys discuss those for not very long, like 4 minutes maybe. All right, I think we got everybody back now. So let's look at this real quick. So first of all, it says the Consumer Protection Agency is testing a sample of cans and tomato soup from a company. If they find evidence that the average level of the chemical bisphenol, BPA, in tomato soup from this company is greater than 100 parts per billion, they will recall the soup and sue the company. So first, we wanted to know the hypotheses. So our null hypothesis always has the equal sign in it. So under the null hypothesis, we're going to say mu is equal to 100. And then the alternative, what we're trying to find evidence for, is going to be mu greater than 100, because it said we want to see if the BPA is greater than 100 parts per billion. So if I think about a type 1 error is rejecting the null hypothesis when the null hypothesis is true. So in this case, we would be concluding that the BPA is higher than 100 when really it isn't, right? So that would be the error we're making. We would conclude based on our test, BPA is more than 100 when really it isn't. And what that would lead to then is that we would recall all the soup and we would sue the company. So that's kind of bad, right? A type 2 error, that's failing to reject the null hypothesis when the null hypothesis is false. So if we made a type 2 error, that would be concluding that we don't have evidence that the BPA is over 100 when really it is over 100. So that's also kind of bad, because then, if BPA is harmful, then we might be poisoning the public and, we don't even know it, basically. So which one of those did you guys think was more serious? The type 1 or type 2 error in this case? All right, few votes for type 2. So you think it's worse to poison everybody than it is to wrongly sue the company and recall all the soup? They're both kind of bad. It's kind of like trying to choose between, I don't know, having your toenails ripped off and having your fingernails ripped off, I guess. I don't know. So two really bad things, right? Okay, let's move on. So because the chance of a type 1 error is alpha, so we said the probability of a type 1 error is alpha, that means that if the null hypothesis is true, then whatever our alpha is, that is the percent of time we'll get significant results just by chance. So even if there's really nothing different than the null hypothesis, if our alpha is 5% of the time we're going to get significant results purely due to chance. So if 100 tests are done with an alpha of 0.05, then, and nothing is really going on, then 5% of them are going to yield significant results just by chance. So in other words, we'd expect 5 out of those 100 tests to come up significant, even just by chance. So this is known as the problem of multiple testing. And the problem is that it's not that uncommon to have multiple tests going on all the time. So we could have a topic that's being investigated by research teams all over the world. We might even, so if we do that, then, even if nothing is happening, even if the null hypothesis is true, 5% of those teams are going to find something significant. Similarly, if we have a research team or company that's doing a lot of hypothesis tests, then 5% of those tests are going to be significant, even if all the null hypotheses are really true. So if thinking back to our mate choice and Offspring fitness example, remember we said that they did that same thing 10 times a day for 5 days. So really their experiment was comprised of 50 smaller experiments. And if they looked at the p-values individually for each of those 50 smaller experiments, then this was all the different p-values that they would have gotten. And if you look here, you can see all kinds of different values. So we can see something really, really small, 0.0001, which we would be like, oh, that's super significant, right? Definitely, mate choice is better. And what would happen if we only published our report reporting this one run and not all the rest of them? And is that ethical to do that? Okay, here's another one here. If we looked at just this one had a p-value of 1. So that's like the opposite, like completely not significant, like no evidence whatsoever that mate choice has an effect on the offspring. So you can see that of these 50 different p-values we got the whole gamut. Okay, so how is this going to affect things in the world? Well, the tendency for people in general is, and really, like if you're a journal or something, like, are you going to get all excited if somebody sends you a study and they're like, hey, we did this study and we found out nothing's going on? Like, is that like, ooh, rush to the presses, let's print that? Probably not, right? That's probably like, we don't care. Like journals and magazines and stuff, they want evidence. They want significant results, because that's exciting. Then you can be like, look, we found significant results of this happened, instead of saying, hey, I did all this work, I did all this data, and I had no evidence. So most of the time, the things that get published are the significant results. And if you have a situation where there's lots and lots of tests that are conducted, then we know that some of those are going to be significant purely due to chance, even if the null hypothesis is true. So what if we're only hearing about these studies that were significant, but it turns out there were so many tests done that these were the significant ones purely due to chance? Then we can have some misleading results. It's kind of a problem. And that kind of sounds like, oh, wow, these researchers, they're like terrible people. Like, why would they just publish the significant ones and ignore all the other ones? But like, honestly, that's human tendency. So I want you to think back to your last post on Instagram or Facebook or TikTok or whatever social media platform that you use, and think about the picture that you posted, and then think about how many pictures you took that you didn't post on there, and how maybe those pictures were different from each other. So I went back in my files back to when my Quints were little, and one year for Halloween, they were the 5 little monkeys jumping on the bed. And we were trying to get a picture that we could use for to put in a calendar. And so I was trying to herd them into taking a good picture for me. And like, these are like the pictures that I was getting. Like, they were just falling all over the place. They were throwing things on the floor. They were falling off the bed. And I took, I forgot to write down the exact number. It was around 150 pictures that I took to finally get one good picture that I actually published in, or that I actually put into my calendar. So, this idea of the publication bias, like it's not a new idea, and we all do it, but that doesn't make it good, especially in a research setting like this. And some of these people might not even know. If people all over the world are testing it and like you get this significant result, you might be like, woohoo, I got a significant result, published. But we need to be aware of this. You need to be aware of this. And it should make you a little bit nervous and a little bit scared about the results that you read. So we know that alpha of all tests with the true null hypothesis will yield significant results just by chance. So the one that happens to be significant is the one that's going to get published most often. And so we should be nervous about that. So what can we do? Well, realize, first of all, that errors are possible. Again, we're only looking at sample data. So of course it's going to be possible that we could be making a mistake, or that the researchers could be making a mistake. Realize that multiple testing and publication bias are actually a huge problem right now, and probably will continue to be. But now that we have all this knowledge behind us, now that you took this fabulous statistics class, you can recognize and be skeptical when a claim is one of many tests. And you can look for replication of results. So replication of a study is when you're able to basically reproduce the whole study and get similar results in another setting. So studies that have been replicated with similar conclusions gain credibility, and studies that have been replicated with different conclusions lose credibility. And replication is going to help guard against type 1 errors, and it's going to help us with generalizing, essentially. So the key points that I wanted you to get on this one were kind of what replication is, and the idea that, and these two things here, just that if you can find studies that have similar results, then you can be like, okay, maybe I can actually believe this. And if you see studies that have varying results both ways, then maybe you'd be a little bit more hesitant to believe that. All right, so looking back at this mate choice and offspring fitness study, so there was actually multiple experiments that were done. So first of all, we have the original study that was significant in favor of choice. Then they had the follow-up study, the one that we talked about most today, that was not significant at all, had a p-value of 0.1. Then they did another follow-up study that was actually significant the other way. So that one said, hey, these little larvae, they do better when the parents are forced into a arranged marriage here. And then a third follow-up study was done that ended up being significant in favor of no choice. So kind of given all these different follow-up studies that were done, do you think that mate choice improves offspring fitness? Do you feel like there's something there, or do you feel like, I don't really think it matters if these fruit flies get to choose who they hook up with? Yeah, I kind of agree with that. Like, I kind of think, hey, the results seem kind of questionable to me. We're seeing studies that kind of go both ways. So I really feel like, it doesn't seem like there's really that much there. All right, so a couple of questions to think about now that we've talked about all this stuff. These are a little bit review from what we've talked about today. So how can we reduce the probability of making a type 1 error? So what can we do to reduce the probability of making a type 1 error? So Will says increase the sample size. Increase the sample size is the answer to a lot of questions. But if we couldn't increase the sample size, or even if we did increase the sample size, there's something we specifically do to set the value of a type 1 error. So what is the probability of a type 1 error? Maybe that'll help you figure it out. Yeah, change alpha, right? So if I want to reduce the probability of making a type 1 error, then I'm just going to use a smaller alpha, a smaller significance level. So I want to decrease the significance level. Okay, how could I reduce the probability of making a type 2 error? Okay, not increasing the sample size is not an option. Okay, remember type 1 and type 2 errors, they're on that little scale. So increasing one decreases the other and vice versa. So if I want to reduce the probability of making a type 2 error, then I could increase the probability of making a type 1 error, which means I would increase the significance level. So if I want to reduce making a type 2 error, then I use a higher significance level. And if a type 1 error is really important, then I'm going to use a lower significance level. So this just shows a little chart here, significance level and errors. So alpha is where we make our decisions, and we're going to reject. If we reject, we could be making a type 1 error. On this side of things, we would fail to reject, so we could be making a type 2 error. So if a type 1 error is bad, then we're going to decrease alpha. And if a type 2 error is really bad, then we're going to increase alpha. So back to that blood thinning drug. Let's say that the new drug has potentially serious side effects. Then what kind of significance level should we choose? Yeah, if the new drug has pretty serious side effects, then we basically only want to reject when it's really, when we should reject. We don't want to switch to the new drug unless it really has benefits that outweigh the bad stuff. So a type 1 error would be pretty bad if it has bad side effects. So we'd use a small significance level. And if the new drug has no real side effects and costs less than the old drug, then maybe we would go with a larger significance level, because type 1 error is not that bad. And so we're going to increase our significance level, have it, and that'll give us decrease the probability of a type 2 error. So we're more likely to be able to detect smaller differences. Okay, and how do we reduce the probability of making a type 2 error? Overall, if I have these two choices, we're going to increase the sample size, so bigger sample size. So if I have a larger sample size, then it is going to make it easier to detect differences, which makes it easier to reject the null hypothesis. So a bigger sample size is going to make a type 2 error happen less often. And it's going to be able to make us so we can detect smaller differences or departures from the null hypothesis. So with small sample sizes, then even large differences or effects might not be significant. So we might not be able to detect those if our sample size is small. So you would think that just being able to take a really big sample size would solve all of our problems, but it doesn't actually solve all of our problems. When I have a really big sample size, then I can detect really, really small differences, which is fantastic, except that sometimes those really, really small differences, while they might be statistically significant, they might not be practically significant. So we're going to skip that little exercise and go to the bottom part of your notes page where it's talking about statistical significance versus practical significance. Okay, so scenario. Suppose that we have a weight loss program. They recruit 10,000 people for a randomized experiment. They assign them to 2 different diets and they follow them over the course of 1 year. And at the end of 1 year, we find an average weight loss difference of 0.5 pounds. And it's statistically significant. Remember, if you remember from when we defined statistically significant means unlikely to occur due to chance, and that we had a small p-value. So in this case, we found a small p-value. The difference between the two groups is only a ½ pound, but it had a small p-value. It was statistically significant. But if you think about that difference of a ½ pound, practically in real life, is it different? Is that going to make you choose one diet over the other diet if after a year, the difference in weight loss was only a ½ pound? Especially if one of the diets is like really restrictive or something. Would that like make you sign up for that diet? No. Okay, because even though it was statistically significant, practically a ½ pound is not enough to worry about. Okay, there it is, practically significant. So a statistically significant result is not always practically significant, especially with large sample sizes. Okay, so on your paper where you're trying to write something down, this is what I want you to write down. Okay, so this last bullet point here. So write that down under statistically significant versus practically significant. Okay, and then remember that statistically significant has to do with the numbers, essentially. Okay, so it's small p-value. So statistically significant basically equaled small p-value. Okay, whereas practically significant says, okay, is this difference meaningful to me as a researcher? So practice, this is where you put your first, second bullet. So practical significance, that was a C, is whether it's meaningful, if the number is actually meaningful in the context of the problem, basically. So it's whether the number is meaningful in context. Yeah, all your pictures on this side, it's not letting me write there. So this is context. So kind of to sum up what we've talked about today, okay, first of all, we said, conclusions based on p-values, they're not going to be perfect. We can make errors, okay, and we've talked about type 1 and type 2 errors. We talked about the fact that alpha percent of all tests will be significant just purely due to chance. And sometimes only significant results get published. So it's possible that some of the things that are getting published were really, type 1 error type of things where they really weren't a deal. And yet we're saying, yep, look, significant evidence here. So we have to be aware of that. And because of that, we're going to look for replication of results when we read about something in a journal or something like that. And also in the end here, we talked about how large sample sizes make it easier for us to get significant results also. So we always want to look at statistical significance versus practical significance in the context of our problem.